Okay. Section 4.4, concavity and curve sketching. There's one more thing we need to learn about curves before we put together some very pretty pictures, and this concept of concavity. So when you read here, on the left and right sides of the curve, here and here, the curve faces up or would act like a bucket or hold water. We say that on the left and right, this curve is concave up. In the middle, the curve is facing down. It would not hold water, would act like an umbrella, or it's frowning, concave down. I like the frown analogy, down and frown, smile. Or frown and down, they rhyme. Up looks like a smile, frown, down. We say the center of the graph is concave down. Visually, a curve is said to be concave up if it holds water, acts like a bucket, or looks like a smile. Visually, a curve is said to be concave down if it wouldn't hold a water, if it's an umbrella, if it's a frown. Now, these certainly aren't official mathematical definitions. The official mathematical definition has to do with the first derivative. That's a little bit beyond what we need. We just need to know what it looks like. Concave up curves look like they're smiling. Concave down curves look like they are frowning. And where we change concavity, either up to down or down to up, smiling to frowning or frowning to smiling, those are inflection points. So using the graph given above, estimate the interval where the curve is concave up, concave down, inflection points. So we'll do concave down in blue. And it looks like we're concave down from there to there, and right out back there. So concave, those are up, excuse me, concave up in blue. And so it looks like we are concave up on negative infinity to negative 1, 1 to infinity. If I was being a perfect math teacher, I'd put union symbols between those. Concave down in the middle. And then where I change concavity are my inflection points. So we'll make great big green inflection points. In green, inflection points. And so it looks like we have inflection points at x equal plus x equal plus or minus 1. Okay, so we want to be able to find these things better than just estimating from a graph, because actually our goal is to produce the graphs, not have the graphs and answer the questions, but produce the graphs. So some facts here. If f double prime, the second derivative, is greater than 0, if the second derivative is positive on an interval, then the curve is concave up. Second derivative positive, concave up. If the second derivative, f double prime, is less than 0, if the second derivative is negative, the curve is concave down, and then possible. It's bold, it's capitalized, it's underlined multiple times. Possible inflection points are located where the second derivative equals 0 or is undefined. Possible inflection points. Just like critical numbers can turn out to be maxes, mins, or nothing, possible inflection points can be inflection points or not. It depends. You've got to verify whether it's an inflection point or not. Now, the good news here is you actually already know how to do these problems. You just don't know that you know how to do these problems. You do know how to do increasing, decreasing, local max min. Increasing first derivative positive, decreasing first derivative negative. Max mins, critical numbers. Critical numbers, first derivative equals 0, first derivative undefined. Look at how similar this is. Instead of first derivative positive, we have second derivative positive, concave up. Instead of first derivative negative and decreasing, we have second derivative negative and concave down. And instead of critical numbers, where the first derivative is 0 or does not exist, we have possible inflection points, where the second derivative is 0 and the second derivative does not exist. And so we're going to do all the exact same stuff we did in the last section with increasing, decreasing, and critical numbers, all that same sort of stuff, but we're going to do it now with the second derivative and call it concave up, concave down, possible inflection points, and inflection points. But the steps are going to be the same. And so how to find intervals of concavity, how to find inflection points. Anytime you read those instructions, here are our steps. Find the second derivative. Find the x-coordinates of possible inflection points. A, set the second derivative equal to 0 and solve. B, if the second derivative is a fraction, set the denominator of the second derivative equal to 0 and solve. Just like you would with critical numbers, but with the second derivative. Then 3, make a sign chart in the exact same way we made the sign charts before, but using the second derivative. 4, label each interval as concave up, concave down, concave up if the second derivative is positive, concave down if the second derivative is negative. 5, identify any inflection points, and then define the y-coordinates of inflection point, substitute the x-coordinate of the inflection point into the original function. So doing this first problem, determine where the function is concave up, where it's concave down, find inflection points if any. So here's my original function. Let's simplify this first, but let's also note this is undefined at x equals 0. If I try to put a 0 in there, I'm going to have division by 0. Division by 0 is a horrible, horrible thing. Can't happen. And so it's undefined at 0. And so what this tells me is that there will be no point on the graph when x equals 0. Now, if we were to fully graph this one out, we would find that there's a vertical asymptote, but there doesn't have to be a vertical asymptote just because we're undefined, and we'll talk about that later as well. But because it's undefined, we're not going to have a point there. Now, let's simplify this first. You could use a quotient rule on this, but let's just remember when there's one term in the denominator, my best bet, I'll write that down on the next line. My best bet is to split it up. So my original function is the same thing as 10x cubed over 60x to the 5th minus 25x squared over 60x to the 5th plus 24x over 60x to the 5th minus 8 over 60x to the 5th. And what that's going to give me 1 over 6x squared minus, divide both those by 5, 5 over 14x cubed. 60 divided by 5 is 4. No, it's not. I can't do that in my head. 60 divided by 5 is 12. I should have known that. Plus, divide both those by 4, or divide those both by 12. That'll give us 2 over 5x to the 4th, dividing by 12. And then minus, divide both those by 4, 2 over 15x to the 5th, if I didn't make any mistakes. And here's one of the times I really miss having a classroom full of students who would have yelled at me if I had made any mistakes. So let's check this. So you check all this stuff twice. So 10x cubed over 6x to the 5th, 60x to the 5th, minus 25x squared over 60x to the fifth, 24x over 60x to the fifth minus 8, divide by 10, 1/6 x cubed, divide by 5, divide by 12, yeah, and divide by 4. Okay, that looks good. And let's rewrite that one more time to 1/6 x to the negative 2 minus 5/12 x to the negative 3 plus 2/5 x to the negative 4 minus 2/15 x to the negative 5. So it's still the original, but in a much more calculus-friendly format. So now my first derivative is going to be multiplied by that exponent, so that's going to be negative 1/3 x to the negative 3 plus, multiply by the exponent, so it's going to be plus, the 3 and the 12 are going to cancel, leaving 4. So 5/4 x to the negative 4 minus, multiply by the exponent, 8/5 x to the negative 5. And then multiply by the exponent, so it's plus. The 5 and the 15 are cancel, leaving 3, so plus 2/3 x to the negative 6. There's my first derivative. Move right on to the second derivative. And my second derivative, multiply by that exponent, so it's going to be positive. And so I'm going to have x to the negative 4, multiply by the exponent, decrease the exponent by 1, multiply by the exponent, the 4's are going to cancel, and then it becomes negative, decrease the exponent by 1, negative 5, multiply by the exponent, so those 5's are going to cancel, but it's going to become plus, 8x to the negative 6, multiply by the exponent, so that 3 and the 6 are going to cancel, leaving a negative 4x to the negative 7. And there's my second derivative. Check these things twice. I believe I am good, but you should check these things twice. Now, I'm going to draw a line through the first derivative, only because we no longer need, for concavity, we don't need this anymore. Concavity is entirely about the second derivative. Once you get to the second derivative, you ain't looking back to that first derivative for any information at all. So we're just going to draw a line through it to remind us not to use it. And then because we're about to switch to algebra, I'm going to go to positive exponents because I prefer positive exponents when I'm doing algebra. So there's my second derivative. Now I'm going to find my possible inflection points. So step 2, possible inflection points. Set the second derivative equal to 0 and solve. So 1 over x to the 4th minus 5 over x to the 5th plus 8 over x to the 7th plus 4 over x to the 7th. Made a little typo there. Equals 0. Clear the fractions. So multiply everybody by x to the 7th. And so we're going to cancel, get x cubed. So we have x cubed, cancel, leaving behind an x squared. So minus 5x squared. Cancel, leaving an x, plus 8x, and cancel, plus 4, equals 0. And we will finish up this equation, cliffhanger, we will finish up this equation on the next video.